because you have too many. Yeah. Yes, that kind of thing. Yeah, but those are things you want to learn to do when you're engineering. So it's easy to look up the numbers. It's easy to look up the equations, or easy to look up some numbers, but then you got to figure what those numbers mean. What the numbers mean, and how to manipulate those numbers so you can either design or build or make something. Okay, so anyway, let's do the oxidation half reaction. Okay, so let's see, we said that the oxalate is being oxidized. Okay, so note that the carbons are not balanced on each side of the equation. Let's put a 2 here. Now, how many electrons is the C2O42 minus ion losing? Okay, so note that we said that one carbon has a +3 charge, and it goes to a +4 charge here. Okay, so we put a 2 here. That means 2 carbons is +3 times 2 is +6. So it goes from a +6 charge to a +4 times 2 is +8. So +6 to +8 is 2 electrons. We put 2 electrons here. So that means the oxalate ion is losing 2 electrons. And is this equation balanced? Do we have to add water or H plus to balance this equation? Yes, this is balanced here. Is the reverse of this reaction shown in table 19.1? Lewis.
Where did you get the 2 for the CO2?
Oh, because see, we have 2 carbons in the oxalate. We only had 1 in CO2, so to balance that, we have to put 2. That's the concentration of mass. Okay, so this is balanced. It is the reverse of this reaction. That is the reduction reaction shown in table 19.1. Yeah? Okay, so did we balance it right here? Okay, so now we can get our overall oxidation reduction reaction. Okay, so to do that, again, we have to make sure the same number of electrons are transferred. So note that in the reduction we have reaction, 6 electrons are transferred. In the oxidation, only 2 electrons are transferred. So that means that we have to
add 3 more. All right.
not add 3 electrons, but 2. Because 2 plus 3 is only 5. We need 6. So you're not adding.
Oh,
So you're multiplying. Okay, so let's multiply this by 3. And then we can add the reduction to the oxidation. We'll have our balanced oxidation reduction reaction. We have 14H plus Cr2O7 2 minus plus 3 oxalates going to here's our balanced oxidation reduction reaction. And the concentration of mass and the concentration of charge law should be obeyed in our balanced oxidation reduction reaction. Okay, so I'm not going to ask you how to do this on an exam or a quiz, because really I can barely remember how to do it once a year anyway. Because I just looked in table 19.1. Okay, so in acid solution, you add water and H plus. In basic solution, you add water and OH minus. Okay, so that's the only difference between acid and basic solution. Okay, so let's move on from this slide. Okay, so we talked about this last on Tuesday. We also talked, did anyone come with that? I didn't look at this again. Did you come up with an analogy for voltage?
Electric field has displacement.
Pardon? Jeff?
The electric field has displacement.
No, we're looking for an analogy. Current is like the size of a water pipe or broadband versus dial-up, whereas voltage is like pressure difference, like a pressure drop between from one end of your water pipe to the other. You know, there's a lot of pressure. There's a lot of pressure in that where your water pipes in your house just to get that water pumped. Okay, we looked at this last time. And let's see. Oh, so you're going to split water in lab today. So let's figure out how to do that. So we talked about voltaic cells, and let's just go back quickly to here. So in a voltaic cell, that uses chemical energy to make electrical energy. Electrolytic cell is reversed. You use electrical energy, that is, you supply electrical energy to make a chemical reaction occur. That means that you supply electrical energy to make a non-spontaneous reaction occur. Okay? So how are we going to use an electrolytic cell to split water? Okay, so we know that if you have this reaction, H2 plus O2 to make water, is delta G for this reaction greater than 0 or less than 0? Greater or less? So by saying greater, you mean it's non-spontaneous, the reaction doesn't occur. Less than 0, it is spontaneous, it doesn't occur. Yeah, in this direction, as written. So this reaction is spontaneous. So when hydrogen reacts with, when hydrogen is placed with O2 gas, and then there's a spark, does the H2 and O2 combine together to form water spontaneously? Once it overcomes the activation energy. So is delta G greater than 0 or less than 0? Yeah, so this is spontaneous reaction, so delta G is less than 0. Now, when you split water, you're doing the reverse. You have H2O going to H2 plus O2. This means that delta G for this reaction is going to be greater than 0. This is a non-spontaneous reaction. So what you're going to do, you're going to supply energy to make this reaction occur. Okay, so let's figure out how to do that. Okay, so you're going to use an electrolytic cell. Here's the start of our cell. So we have, here's our container, which contains some liquid in here. We have 2 electrodes. We have this. What's this supposed to be? This will be our battery. Our battery is going to supply, electrical energy. Okay, current and voltage. So what do we want our electrodes to be? What do we want in the solution? And what is the minimum voltage we need to split water? Okay, so first let's start down here. So what should be in here? Yeah, there should be water in there. Now, I have this question, would you add anything to the water? Why would you add salt? Yes, you want to have an electrolyte in there. Now, you want to choose the electrolyte so that that electrolyte you add is not oxidized or reduced at each electrode. So, for example, if you put sodium chloride, is sodium ion going to be reduced to sodium metal, or is chloride ion going to be oxidized to chlorine gas? Okay, because if that happens, that's going to slow down. That's going to compete with these water splitting reactions. Okay, so you don't want that to happen. Now, have you ever split water before?
Yes.
And when and where did you do it?
Yeah.
Okay. You use salt in it? Did you put salt in it for humidity in your glass?
No.
Okay, what did you use?
I can't remember. I usually just use water. You powered a car with it.
Now, have you ever seen in your car battery bubbles forming from one of the or both of the electrodes? Yeah, that's not a good thing for your car battery, because then you form hydrogen gas. Hydrogen and oxygen gas are in each electrode. So actually, depending on the condition of your car battery, you can be split in water, which you don't really want to do. So, what's the electrolyte in your car battery?
What kind of hydrochloric acid?
Yeah, sulfuric acid. So sulfuric acid is commonly used as the electrolyte to split water. Okay, so you would not want to use water here because water is a poor conductor. There's not many ions in there. So that would be, if you use this water only, you would have to use a lot of energy to get the ions to move from one electrode to the other. Like, in other words, your ionic current between the electrodes in this liquid would be really low. You want actually a high ionic current. Okay, so in other words, not only do you want electrons flowing through the wire, you want ions flowing through your solution here. Okay, so you can either use commonly sulfuric acid, or if you want to use a base, you can use sodium hydroxide. Okay, so either one is used. What would you want to use for your electrode material? So would you want to use something which is, for example, a metal which is easily oxidized? Because if the metal is easily oxidized, then the metal ion is going to be in the solution, and that can be reduced at the other electrode. So do you want that to happen?
No.
So you would actually want would you want an active metal or an inactive metal as one of your electrodes? And you want an inactive metal, so often platinum is used, or gold as your electrode. Or if you want to use an inert electrode, you can use carbon or a graphite electrode. Okay, so for your electrodes, you can use either platinum or gold or graphite. So we actually have, in the lab, we actually have graphite or carbon electrodes which you can use. Now, how much voltage do we need to apply to the cell to split water? And before we answer that question, we should figure out what is the oxidation half reaction that occurs and what's the reduction half reaction that occurs. Okay, so let's do that. Now, let's take a look at table 19.1. And in table 19.1, let's try to find an oxidation and reduction half reaction to produce H2 and O2. So let's take a look at that. Let me erase these. Now let's try to find some reactions here in table 19.1. Oh, so actually I just erased them. So let me write this one back to the chalkboard. We have O2 plus 4H plus 4 electrons, and that's producing H2O. So note that 2H2O. So note that this is a reaction which O2 is being reduced to H2O. And then the reduction potential for this reaction that's equal to, let's see, that's equal to plus 1.23 volts. Now note that with H plus, this is done in an acid solution. Okay, so do you see any other ones with either O2 or H2? So there's one O2 plus 2H plus 2 electrons going to H2O2. Let's not do that because we don't want to make hydrogen peroxide. Okay, so we'll skip that one.
NO3.
Bruce?
NO3.
NO3?
Plus 4 NO3.
Which one is that one? What's the reduction potential?
Plus 0.96.
Plus 0.96. Well, this will work. We have nitrate ion solution. Are we going to have nitrate ion in solution? Yeah, so let's not use that one because there's nitrate. We're not going to have nitrate in solution here. There's one at this one. Here's O2 plus let's see, plus 2H2O plus, let's see, plus 4 electrons, and that produces hydroxide ion. There's, let's see, 4 OH minus, and note that in this case the reduction potential is equal to 0.4 volts. Now note that OH minus is here, so this is done in a basic solution. Okay, so this is an acid, this is in base. Let's keep on going. There's another one at, let's see here. There's one, and there's this one. We have 2H plus 2 electrons going to H2. And this is our reference. This is 0 volts. So with H plus here, this means we're doing it in conditions of an acid. And then if we keep on going further down the table, let's see.